Okay. Sorry, just let's start as a slideshow. Okay, so hi everyone, my name is Esther Vicloli, as Gabor already introduced me. And this talk or this presentation is a paper review. The title of the paper is way longer, but I will just refer to it as RuleNN or Rule Neural Network. As Gabor already mentioned, a combination of rules and neural networks. And the model or the system that they developed, it's called RuleNN, so that's why I also call it this way. The paper is from 2020. It was published in the conference of the EMNLP, Empirical Methods in Natural Language Processing. And most of the authors are from IBM and Google. So yeah, quite. It's IBM is obviously also means that part of the data and code is not publicly available. So yeah, it has also drawbacks, but big names, big people. And the title is Learning Explainable Linguistic Expressions with Neural Inductive Logic Programming for Sentence Classification. So what this is about, a brief summary. The main topic is transparent learning. So as opposed to black box learning, this learning should be interpretable and explainable for humans. The task, as already mentioned in the title, is sentence classification, actually binary classification. The model which is used, it should be interpretable. So it's actually a mathematical model, nothing else than first order logic rules. We will see it later. And the method which is used is actually neural network. So we'll see how neural network can still be combined with interpretability. The results are quite convincing and quite promising because the results of this rule neural network outperforms most of the statistical and neuro-symbolic methods, and also comparable to recurrent neural networks. And the big implication of this whole study is that actually it is possible to create explainable and editable models, which can actually have a lot more business cases than just simple black box models. Okay, so just to put it in context, what's the problem with black box models? So traditional black box models are mostly deep neural networks, and also big natural language models like BERT. They are very difficult to interpret, and they learn undesirable bias, like they can learn pretty fast to be sexist or racist and so on. And there is a need for interpretability. Of course, we don't want to develop such systems that are biased against minorities or in whichever context. And attempts happen now, until now, to explain models. They either happen by surrogate models, which means to create a kind of substitution model, so not to explain the model itself, but a substitution of it. And one really frequent thing to do is to analyze the weights, or like the attention weights in neural networks, and call it as an explanation. But it does not mean that the model itself is explainable or that the result is editable, by far not. Or it just means that the weights somewhat correlate to what we would expect. So the knowledge gap is actually there, whether these surrogate models correctly reflect the whole procedure. And as I mentioned, like this weight analysis is kind of an afterthought in the question of explainability. So you train a model, you have your weights, you have your model, and after that, first, only after, you want to explain that why it's working like it does. And the aim would be to treat explainability as a first-class citizen, so to say, from the beginning, by design. The research question of this paper is the following: is it possible to devise a neural network that directly learns a model expressed in a clear human readable dialect? And we will see that the question is yes. And they also suggest an approach. So this is the very, very high level picture of their whole system. You can see RuleNN in the middle. It has some kind of pre-processing part with the natural language unit, the NLU unit, and also some kind of post-processing verification part. The whole system takes as inputs dictionaries and sentences. The sentences are obviously coming from the task itself. And the dictionaries, they are handcrafted. We will see how they look like. Then this first natural language processing unit will process the text and convert it into this logical formulae, facts and predicates. They are the mathematical terms for facts and predicates, which will serve as the input for the RuleNN neural network. Then this neural network creates the so-called LEs, linguistic expression. You will hear this term a lot, which will be verified in the end, and then we get our final linguistic expressions. So the idea basically is to model natural language processing with first-order logic. It is first-order logic formulae. Also use some kind of semantic parsing, which will serve for constructing the predicates. And yeah, so from the combination of maths and linguistics, so kind of the first-order logic formulae and the semantic parsing output, this neural network will create linguistic expressions which will be human interpretable. So what are they? I will start right away with an example. This is one sentence. Notices may be transmitted electronically by registered mail. You can see this so-called shallow semantic parsing. I will tell you more later on, but you can already see that basically the verbs or the actions of this sentence are found or identified first, and then there will be some connections between the rest of the sentence. They will be the so-called arguments. And the linguistic expression itself is a kind of rule. So that's what we call a rule within this RuleNN neural network system. So the learned rule is actually a clause. So you can see on the left-hand side, communication, that's a label. So this whole thing means that a sentence S will be given the label communication if the right part, if the clause on the right side holds true, which has several parts. Like you can see, it's actually a conjunction of 3 different predicates. And you can see that the verbs itself, like notice, inform, or transmit, they appear within this formula. So it basically means, just to get a bit ahead, A will be an action. We will be dealing with sentences and actions, and the actions are actually just the verbs within the sentence. So this basically means that I will assign the label communication to a sentence if this sentence has an action A, for which is true that for this action, the first argument is notice. You can see it applies above. And this action, it's a verb. This is a verb, and this verb is either inform or transmit. And you can see if we pick the verb transmit, then the A1, the first argument of this verb, is notice. So it's the surface form. Of course, we will treat lexemes and not conjugated forms. And this verb is inside the sentence, so this will be assigned communication. Well, I think it's probably not so intuitive, but after a short explanation, you can actually interpret this formula and see why communication is assigned to this sentence. Okay, this is the high-level overview of the whole system. We will take a deeper look into each part of this, but just to so that you can be aware and think ahead. We start and at the left-hand side with the inputs. As I already mentioned, we will have sentences and dictionaries. So dictionaries just basically sets of words. And it's actually a bit unclear to me how they are constructed. I read that they are handcrafted, so someone put a lot of work into it to create these dictionaries. Actually, for one dataset and for the other dataset, they applied some kind of semi-automatic way, but it wasn't described in the paper. So let's just assume that dictionaries already exist. They come as input. Then this natural language understanding unit, it does multiple things. First, it parses the sentences semantically, but I think actually also syntactically. Anyways, we will get these semantic relations within a sentence. And we also in the dataset, all the verbs called actions will be found. And then some kind of facts and predicates will be constructed. We can also represent them as a matrix, more later to that. So this matrix, now we're dealing with numbers, they will be fed into this neural networks, into this neural network, which will learn some parameters called alpha. And after that, so this neural networks has an output. What the neural network has as an output, they already just they just wait as always, so they are not quite formulas. So that's why we have this full first order logic retrieval algorithm as a post-processing step, which will return these predicates in the form of linguistic expression that I just explained in the previous slide. So that's the big picture, and now let's dive into it. Okay, I mentioned that I will just tell you a bit more about this shallow semantic parsing part, because I think since that's the main, that's what comes out in the end, it's important to be able to understand them. You've probably heard about syntactic structures. It's just basically the bracketing of text, or you probably have seen it in the form of a tree. And this was the most famous data source for this is the so-called Penn tree bank. And the proposition bank is actually built upon this Penn tree bank, built upon this syntactic parsing or this syntactic labels. So sentences are not just assigned to syntactic categories, but also some kind of semantic rules, and that's how this propositional bank dataset was created. It's shallow because it does not contain any higher order phenomena, like there's no coreference resolution in it. It's just basically a predicate argument information within the sentence, where we have two kinds of information. First, we have numbered arguments. The arguments, you already saw that they just number, like zeros argument first and so on. So they are not called anything like agent or any linguistic category, because I think the authors wanted to keep it as simple as possible and also flexible to be able to map to any specific linguistic theory. And the other kinds of arguments, the other kind of information is the so-called adjunct-like arguments. They hold supplementary information for a specific verb or for a specific action, like the location, cause, or time. They are mostly parts of a sentence that could be omitted and the sentence would still make sense. And this is just an example what kind of information we have in this propositional bank. We have informations for a lot of words, I think a couple of thousand. And one single verb can have multiple meanings. Like in this example, they call frame sets. We have the verb decline, and it can either mean go down incrementally or demur, reject. There are different meanings, so obviously the arguments are also look different. So in this propositional bank, in this database, for every single meaning of a verb, there are arguments defined like quite individually. So like in the first case, the first argument is the entity going down. You can see in this example, like its net income declining 42% to 121 million in the first 9 months of 1989. So we find the verb declining, then we can see the entity which is going down is its net income, the amount is 42%, and so on. But those arguments could not be applied for the second example, which is a spokesman declined trace to elaborate, because there's like no entity going down. But what we have instead is, for example, an agent, which is the zeros argument. Don't ask me why up there's no agent, there's no zeros argument. I don't know why the numbering starts with 1 and in the other example with 0. But anyway, I think you get the gist of it without knowing any more about linguistic stuff. So we already touched the linguistic part, and let's touch a bit the maths part, the first order logic part. It's also called predicate logic or quantificational logic, because first order logic works with quantifications, with existential and universal quantifications. And besides, we have 3 kinds of operators: conjunction, an and relation, disjunction, an or relation, or negation. What is important about this is how we can learn such formulae. What's already been done is applying inductive logic programming, the so-called ILP, statistic learning, or neuro-symbolic AI. Those are actually the authors of this paper. They picked methods from these areas, and they compare their methods to these to methods from these areas. We will see the results. So the knowledge gap so far is that none of these approaches have targeted NLP so far. So that's the big challenge, how we can solve that. Okay, so we solved that, or the authors solved that by linguistic expressions, which is a concept they came up with. This linguistic expression, I already explained to you that they are human interpretable and so on, and they consist of different parts like semantic predicates, syntactic predicates, and the distinguished predicate. I will just want you to have this picture, and some slides later, you will have the meaning for that as well. Okay, so let's build up step by step what a linguistic expression is. Let's start with the math. So with a logical predicate, a predicate is just a function returning either true or false, so a Boolean valued function. We call atom predicates. These predicates can take variables, but if these variables denote constants, then we call this predicate an atom. And if this atom holds true, then it's a fact. We will need this term fact later on, so that's why I wanted to define it. Then let's define a certain kind of predicate, the so-called semantic role labeling predicate. This, or also I call them semantic predicates. They hold true if the given dictionary holds the attribute surface form corresponding to a specific semantic attribute. So this is basically that the verbs, the example semantic attributes can be the numbered arguments or the adjuncts or the verb itself. So those are basically the rules that you already seen, but we will say it just in a couple of minutes. We also have syntactic predicates, which do not really have to do with a specific dictionary, but rather with a syntactic attribute. What are syntactic attributes? For example, the tense, whether it's present, future, past, or the voice, whether it's active or passive. And a syntactic predicate is true if the action's value is equal to a specific value of a syntactic attribute, like if the verb's voice is active, it's true if it's active, and so on. So it's not so complicated. Now we almost there. We have a rule. So how a rule looks like. The rule itself has a head predicate and a body predicate, and the head is true if the body holds true. And the body is basically the condition, and the head will be, in our case, the label assigned to a sentence, since we are dealing with binary classification task. So the linguistic expression is nothing else than a clause over a sentence and action. It's very important that one linguistic expression always has two variables, the sentence itself and the action, but the action is kind of hidden. It's implicated that an action should exist for which is true. So it's on an action level that's important. And this so-called distinguished contains predicate. This one is the predicate which assures that this specific action should exist within the sentence. But let's see the example again. Probably, I hope now you get more. Let's start. I think we can start from the left-hand side. The blue one is the rule itself. It's called R3, the third rule, in whatever context. And this is the linguistic exception, which means that we have a rule which has a head predicate. That one is the brown one, which is actually a label, and the body is all the other three ones, like the green ones, the purple ones, and the orange ones. So it means that this sentence S will be given the label communication if this sentence has an action. So the sentence contains an action. This is this distinguished predicate. And after that, we have some semantic conditions with this contains that I just mentioned, that like this action's zeroth argument should contain the verb notice or the word communication. You can see below that this argument is not just one word, it's a complete expression, but notice is contained, so it also holds true. And you can see an example for a syntactic predicate, which in this case is the tense of the verb, and it must be in future, and it is in future, so the label is assigned. You might ask now why it should be in future tense, and that's a really good question, because actually it shouldn't, and that's what, spoiler, but that's what human evaluators did. They actually deleted that part, that third predicate, because the system learned it, but it doesn't make sense. Okay, just a sec. Okay. So let's talk about, I will shortly introduce the data set to you, just to know, just to have a basic idea about this. The first one is this TREC, it's a question classification task. Some of the examples are like, what is the full form of .com? What we're looking for here is an abbreviation. You can see that this data set has main categories like abbreviation and subcategories, like if it's an abbreviation or an expression abbreviated. Actually, the authors of this paper, they did not make any difference between the subcategories, so they only used the big categories. There are certain questions which ask for location or a certain human, like what is the oldest profession, like in that case, we are looking for human title, entities, descriptions, or abbreviations. And you can see that the label distribution is quite skewed. And the last column, this P, it will be also interesting for later. Just to explain it shortly, this P is the so-called set of predicates. And that's the number of predicates, like just to get a feeling for the order of magnitude, how many predicates we have for a label. It's around 100. in this data set, or a bit above. The second data set is so-called contracts. It's IBM proprietary data, so it's not available. It's a multi-label task, but treated as a binary classification. So separate classifiers were trained for each label. The sentences are coming from legal contracts among enterprises. The training set, there's a bit of a difference between the training set and the test set, in the sense that in the training set, IBM is always the first party, while in the test set, we have diverse companies, and the authors kind of claim that, oh, this is evidence for generalization. I'm not sure how far, like to what extent it's true, because it's still the same context. But anyway, they have a very strangely abbreviated labels like W or SOW. You can see that actually you can find the explanation for the labels. I just I picked a screenshot from payment terms and billing, which is abbreviated as P&B in the table, or the famous communication that I showcased before is just abbreviated as C. But we don't really know more about this data, just these summaries. Okay, I think now we arrived to the point of to define the actual architecture of this RuLE neural network. Just to recap again, what are the steps to take? At first, we have to somehow identify or to learn these predicates, also known as the first order logic rules. And you saw that one single LE linguistic expression might have different predicates in a conjunction. So we will separately learn, so-called discriminatively learn these predicates, and then they will be combined into one linguistic expression. And we also learn multiple linguistic expression because, you saw that one single linguistic expression that might not cover all the sentences with a communication label. Exactly. Okay. So this architecture picture, I just put it again. You saw it already once, but probably now it has more meaning for you. And now if we zoom more into this RuleNN part, then it has itself two separate modules. First, the PGM, the predicate generation module, and the second one is the CGM, the clause generation module. The difference between them is one predicate is just like, it's basically one part of this LA. The clause is made up of different predicates, which predicates are combined by a conjunction. So the parts of this AND relation, those are the predicates, and this clause puts everything together into conjunctive normal form. But before that, just a couple of words about this NLU. So I think it's probably everything is just a repetition, but the input, as an input, we have sentences and dictionaries, and the dictionaries are handcrafted for each label. And the output are these generated facts and predicates. Probably this picture can be interesting to you to see again how predicates and facts look like, because so A and B, B is input, is pure input, it's just dictionary. A is done by a semantic parser. It's also, unfortunately, it's not referenced what kind of semantic parser, or they wrote something like an IBM intern system P stuff. I wasn't able to find it, but let's say it just works the way it should. So it parses the sentences, and A and B are so they are constructed by third-party tools or as a pre-processing step and see they are the actual predicates, they part of their main contribution. And I'm also not 100% sure how they generate these, but by any means, I think a possible way to do this is to combine everything with everything. So we have a lot of dictionaries and we have a lot of predicates, like that transmit has transmit has as the zeroth argument registered mail, or transmit has as a first argument notice. Those are all predicates. And you can combine all these predicates with all the dictionaries and create semantic predicates, like the first dictionary contains the verb form of the first meaning of transmit, which is transmit. Or the second dictionary contains the first argument of the first meaning of transmit, which is notice. So such kind of rules. I think those matches, those are facts because they always hold true, and the contains, they're more like predicates because they still have a variable, which is the s. S is the sentence, so we can substitute the sentence there and check if this predicate holds true or not. Okay, but that's what will be the input for our neural network, but you can see that it's still text. So we cannot really put text, feed text into neural network. Somehow we have to create weights or learnable parameters. The first step to do that is to transform everything into matrix, the so-called predicate matrix. It is, so the matrix has, each of these matrix is constructed for a sentence. So they are so-called local variables, not global variables, because for each sentence we create such a matrix, and this matrix has so many columns as many predicates we have, like all together in the whole data set for a specific label. And the rows will be different for each sentence depending on how many actions a sentence has. For example, this previous sentence has two actions, two verbs, transmit and register, with their specific meanings, like the first or the second meaning, coming from the prop bank database. And then the columns are the specific predicates. I think it's highly simplified here because you saw that we have for a label more than 100 predicates. So you should imagine a matrix here, a 2 by 100 or 130 matrix. So each element of the matrix is either 0 or 1, depending on if a certain action satisfies a certain predicate. Because these predicates, they are unary, so-called, so they're either facts or unary predicates. Facts are already, they only have constants, and unary predicates are predicates which have exactly one variable, and this variable is the action itself. So basically, it says that this matches dictionary, the first predicate is satisfied by the transmit verb, and the second one as well, but they are both not satisfied by the second verb register. So we will have such matrices, and you will see this is called M, the capital M. It's either all the cells or all the elements are either 0 or 1, and it's Ri by P dimensional, which means just this R. I haven't put it into the slides, but the R is defined as the actions of a sentence, and the I is just means that it's one of the sentence. And P, the predicates, they are constant. Predicates are global. They are defined for the whole task, but these matrices are defined for a sentence. Okay, now what we will learn. So these matrices, they come as an input, so they are given. And now we will use these predicates. So in this case, let's suppose we only have 3 predicates instead of 130 in the data set, and we want to somehow learn what kind of predicates are good to pick, so that I learn how to classify sentences. Here they apply a linear combination of these predicates, but actually linear convex combination of these predicates. Convex means that the coefficients are they sum up to 1. So you can see that actually the space where we are searching is a convex hull of, actually if we have n predicates, it's an n- dimensional simplex, so-called, like for 3 dimension, it's a 2-dimensional surface. You can see it here. And if the weights are, so they have to, the weights all together have to sum up to 1. And if they additionally 1 hot encoding, then they pick a corner for corner of this convex hull. So they then pick just 1 single predicate. Like we could learn that, yeah, we have 3 predicates, and if we pick 1 and we always check whether that one is true or false, then we have the rule for the label. That obviously would be too easy, but that's the idea behind it. And since we now have weights, we can use neural network algorithm to backpropagate and to update these weights. I put this formula here. It might explain better to you what are these. And by the way, this is called the parametrized predicate, which is nothing else than just a linear combination of all the predicates, a linear convex combination. That convex things means that all these coefficients, these alpha i's, add up to 1, and each of them is greater or equal to 0. And just to emphasize it again, how many weights we have so many we have as many weights as many predicates, because we assign 1 weight to 1 predicate. Okay, so the big picture, I will explain it to you in more detail. You can see the alphas, which I mentioned, or which we saw just a slide before. They are the blue ones. They are in the middle. And that's what we want to learn. But we put these, I don't know if it's gamma or, so we put another so-called auxiliary variable before, and then we apply softmax, and this softmax guarantees that they add up to 1, so it converts them to probabilities, so that those constraints are satisfied from the previous slide. And what happens is that for each sentence, there's this predicate matrix which is fed into this network. This will be multiplied by the weights, the alphas, and then we get some sort of stuff, and in the end we can compare. But let's take a deeper look at it. So as I mentioned, we have, okay, probably just to mention it before we move on, you can see the 2 concepts or the 2 modules they introduced, the predicate generation module and the cloze generation module. And you can see it already that one cloze generation module contains several predicate generation modules. So it's like the predicate generation module is the basic, and you can use several of these building blocks to get a cloze generation module, and you can even apply several of these cloze generation module for a better performance. Okay, now we're there at the predicate generation module. I already talked about these weights. Here's also described a bit more in detail. Like we have local and global variables that I already mentioned. The local means that they apply for 1 single sentence or instance, and the global means that they are global for the whole task, for 1 binary classifier. Yeah, so what happens here is that we have these weights and they will be multiplied. So it's this matrix. In this case, it's just a small picture, a small schematic figure, but you can see that the blue alpha vector means that the label, this specific label, like the communication, contains altogether four predicates. It's not much, but anyway, for this explanation. And in this case, the sentence itself has 3 actions. So what happens, we multiply 4×3 matrix with a 4×1 vector, and we get as a result a 3×1 vector, which vector is the so-called parameterized predicate, and it should encode responses for actions belonging to an instance. It's basically, it's somehow it's weight how for all the actions, how good they are for the current predicate combination. And the goal is that we have at least one positive, one high value, one value, and that would mean that, yeah, there exists an action which satisfies the current predicates. So that's what we want to learn. The second step is this closed generation module I mentioned. It's how we learn different predicates and we want to put them together. We want to have AND relations, conjunctions. It's actually just done like, you know, that 0, 0, and 0, 1 and 1, 0 results in 0, but 1, 1 results in 1. It's not a differentiable function, so it's replaced by an element-wise product, T-norm. It's so-called T-norm. And this is differentiable, so it can be applied in a neural network context. So we take this element-wise product of the different predicates, and then we have one resulting one. That's in this case it's just 2, but we can take 3 and so on. You can see this is defined by this global variable called m, the small m, which is the length of the linguistic expression. It says that how many predicates I wanna put into this AND relationship. It shouldn't be a big number, because then again it's not so interpretable anymore if you have to read like 10 predicates. So in the experimental setup they used 4 for this number. And actually it can also happen that these different modules learned to predict the same predicate, so it's actually up to m predicates that will be contained within the final LE. We can also, as you could see on the big picture, we can have also several of these closed generation module. That's what is denoted by K. And the combination of the different linguistic expressions. So one linguistic expression is learned by one CGM, one closed generation module, because a linguistic expression is a closed. And we can learn the separate ones. And they are treated in a disjunction. So either this one holds, or that one holds, or that one, whichever holds, I will assign the label. And this is a disjunction, an OR relationship. This will be done by a max function, a maximum. But probably you can see here, you can see it better here. So the whole PGMs, they generate an output for every action. They will be conjuncted, so we will have all the rules or all the predicates must apply, and then we learn separate ones and we just concatenate them. Like in this case, we had 2 separate, we wanted to learn 2 separate LAs, and in the sentence we had 3 actions. And we just take the max, and that would be the label. So it basically means if we found an action which satisfies the predicates, then we're done. We assign a label. So we can compare this max output with the label itself, whether 0 or 1, and that's what gives the error, and that's what will be back propagated to the neural network, and these phis or gammas or whatever weights will be updated, and the alphas as well. And that's what we have. In the end, what we learn now are these alphas. They are kind of a weight assigned to each predicate. How important are they? But it's by far not a first order logic expression. So how we can retrieve that? We have this hyperparameter, this M. We want to have predicates, linguistic expressions with the length of the maximal length of M. So this this algorithm is a bit. It's actually this retrieval algorithm is also one of their contribution, and it's exponential in this M, because what they do at first, they let's say we have 100 predicates and we want to have maximum length of 4, maximum 4 predicates within one clause. So what they do, they learn the weights, all the 100 weights, and then they take all the M combinations of the 100 predicates, so all groups of 4, and they take a look at if the associated weights of these 4 chosen predicates within one group, if their product is non-zero, and they do this sort of verification step at the beginning, at the end, which was also depicted on the high-level picture, is, okay, I learned, my system learned that it's a good rule, but they actually test against, and they only pick this rule if there exists at least one sentence for which is actually true. So they don't want to learn bullshit rules. And this is how the algorithm itself looks like. It's the so-called post-hoc learning expression retrieval. We learned we learned alphas. I think M is not. I think we didn't learn M alphas. We learned the number of predicates, or probably it's a different M here. I don't want to question them. But what we do here is that we do a loop for all the groups of M over all the predicates. We take the product of the chosen predicates, and if they're above 0 and we find one example, X is a sentence, and we find one sentence for which it holds true, then we add to this to the output, and the output is the number of linguistic expressions. Just to have a kind of feeling for that, I think they learned around, in the order of magnitude, a couple of hundreds, like 180 kind of learning expressions for a specific label. So this algorithm is actually exponential and has the potential of having exponential lot rules. But since they have this condition, it filters down just to the best rules that actually apply. Okay, some generic details about this algorithm. So we learn, we have 2 metaparameters, K and M. M is the length of the linguistic expression, and K is, for me, is a bit confusing, because the paper says all the time that we learn K LEs, but actually we do not learn if K is 2, that it does not mean that we learn 2 expressions. With the number of expressions we learn, it depends on what this algorithm produces in the end. So it was a bit confusing for me. But anyway, just to know that there's also this K, we have 2 modules, and we can, it's a hyperparameter, how many times we take these modules both. The data is skewed, so they apply negative sampling and also drop out before taking the marks. They zeroed out some of these CGM's outputs. That's this dropout. It's very conventional to do, and it is exponential in M, the algorithm itself, but it's very efficient for small M. And as I mentioned, they only experimented with M is equal to 4, so it's even. For exponential, it's 16, it's still fine, or whatever. So it's still fine for small numbers. Yes, that's their actual setup, with K is equal to 50 and M is equal to 4, dropout, batch size, learning rate, and so on. The optimizer was stochastic gradient descent with momentum of 0.9. Now let's move on to the experiments. They did quite a great job here with comparing the method to different approaches. As I already mentioned, inductive logic programming, Markov logic network, multiple instance learning, neuro-symbolic AI. So this rule neural network is actually neuro-symbolic AI, but they compared it to another one. And they also compared it to black box methods, to deep learning methods. Deep learning methods are labeled as black box and all the others are white box because they're interpretable. And the input is also, for the last one, the bidirectional LSTM, it was actually token based. So this neural network did not get the predicates as an input and dictionaries. It got tokens, and then an embedding was applied on the token. So it's a bit different from the different of an approach. And the predicate means that all these algorithms got exactly the same dictionaries and sentences as the input. Dictionaries and the shallow semantic parsing of the sentences in the form of predicates. Okay. The metric which was used for the comparison is the so-called area under the precision recall curve. Yeah, you're probably familiar with this issue that either you have high precision or you have high recall, and depending on the use case, you might want to have the one or the other one. The best case scenario is obviously both of them are high, but that's highly idealistic. So what we can create is the so-called precision recurve curve, which says for each which says the trade-off, so to say, between recall and precision. So for each recall, I can look up how much the precision is, and I can pick up an arbitrary point, and let's say, yeah, I'm fine with that if the recall is 70%, but I have a precision above 80, that's fine for me. So it's very difficult to evaluate these systems. Like if you only use an F-score or one single metric, it's quite difficult. They're still using just one metric, which is this area under this curve. It's also actually the same as the integral of this curve. The maximum value is of course 1 and the minimum is 0, and we want a curve which is pretty close to 1. So we want to be at this top right area where both recall and precision is high, obviously. Okay, this picture is just an illustration. They didn't publish any of the curves, just numbers. Let's go through all these approaches. I think just very, very on the surface, what they are. So first, the inductive logic programming is basically a logical approach, a mathematical approach, kind of. We have a background knowledge and examples, and we want a program, a logical program that entails all the positive examples, but none of the negative examples. So it's very mathematical because in practice, you do not, like usually you do not have a data which is that clear that either all or none. There is this one implementation, this metagoal MG, which generates only 0 error rules. So I think actually it returns, it does not return any rule for this problem. And there's a noise tolerant version of this, which also, instead of 0 error rules, it tries to minimize the errors, and this is more suited for noisy real world data. And we will see the results later. Just a couple of words about all the approaches. The Markov logic networks, they are like, they are a combination of these probabilistic graphical models and first order logic. So it's like a Bayesian network, but undirected and maybe cyclic. So what you want to learn here is actually just is formulae, and all the formulas have to have an attached weight. It's actually a highly expressive representation, but the drawbacks are that you have to do a lot. You have to search for clauses and also learn the ways between them. And this LSM, this learning using structure motifs, this method actually does not converge for this specific task. And the other one is learns the weights and the structures simultaneously, and it actually performs quite good. A sec. Multiple instance learning is the next one. It's actually a fairly defined task for by Dietrich from the last millennia. The data set itself contains bags of instances, so like set of instances, and the classification task itself is that for each bag we have to it says the classification itself says that for each bag whether this bag contains at least one positive instance or not. So why it is important? Because in our case sentences are actually bags of instances if we consider that one action is an instance. And a label is assigned if there exists at least one action for which the learned predicates hold true. So yeah, it's enough if we have one action. If we found one action for which is true, it's classified true. It's also the difference here is that we have two levels. We have the instance level, which are the sentences, but we do not train the classifier on the sentence level, but instead one level below on the instance level. Like it's the same which is happening here. We are training this classifier on an action level. And there were two implementations compared. The first one, if this multi-instance tree inducer, it's basically, so this implementation actually learns these rules as a tree classifier, and as opposed to classical tree classifier, tree decision tree learners, it uses a so-called best first node expansion strategy. It is done because since we wanna learn this classification on an action level, an instance level, or like yeah, let's talk about our use case in action level, not the sentence level. The traditional algorithms would not result in the best score. So and there's this other one, this multi-instance rule induction. It works similarly, but the output is more natural set of classification rules. Like the output is more like if-then rules. And the next topic is the neuro-symbolic AI. Neuro-symbolic AI basically means that it's an approach where traditional rule-based AI approaches are combined with modern deep learning techniques. That's what we just see now. So this neural network is also neuro-symbolic. One implementation that the system was compared to is this so-called neural IP, where the problem is to learn probabilistic first-order logic rules, which means the first-order logic rules, and probabilistic, it means that structures of first-order logic rules has to be learned, and the probabilities has to be learned. Probabilities have to be learned, which are the parameters, and this is kind of end-to-end implementation. I didn't look deep into this one. And finally, black box method. You're probably most familiar with these ones. The MINet is a neural network which was created for this multiple instance learning task. So it's quite adequate for this task as well. And the bi-LSTM, I think it was constructed by them. It's just a regular bidirectional LSTM network which gets tokens as an input, and the tokens will be replaced by glove embeddings. The labels are assigned or are defined as the aggregation of the hidden layers. They experimented with different setups for the hidden layer units from 200 to 600. That's why we have in the results a kind of deviation or certain area for the results. And we must note that this neural network, this bidirectional LSTM, has an order of magnitude larger parameter set than the RuleNN. So this is a bigger neural network with way more rules, more resources, more time to train, and so on. And yet, let's take a look at the results. This one big summary table. Yeah, probably first let's talk about these this kind of like the specific things on this. These squares, white squares and black squares. Black squares means black box approaches. White square means white box approaches. We have the predicate base, and the only one not predicate base is the LSTM. The bold ones are the best performing results altogether, and the underscored are the best performing predicate-based methods. It's also it's the same metric. It's the area under the precision recall curve, which you can see here. And you can see that, for example, this MG, which was from this inductive logic programming, this very ideological, either all apply or not, it did not return any of the rules. Or you can see this LSM, which was one of these Markov logic networks, and it just did not converge for this contracts data set. And besides, you can see that this rule neural network results in the best performing predicate-based algorithm, except for one label in TREC, and it even outperforms the LSTM for on a couple of labels, but the LSTM still looks to be the best one. But these are just the comparative results. The quantitative results, they actually did some post-processing human in the loop training, kind of. Let's see. First, let's talk about a bit of explainability. Unfortunately, it's really difficult to find an objective measure for explainability. What they did is quite similar to what Adam's tool also does, a graphical user interface for filtering and ranking these learning expressions based on precision and recall. I think you all used Adam's tool, so you can imagine what it was. There wasn't any link or any screenshot. I don't have a clue how this graphical UI looks like, but apparently people were able to filter and rank and drop or add predicates. So to edit these predicates and to run re-evaluations and see how a change affects the results. And this human in the loop learning, what they did was that they contracted 4 data scientists with a knowledge of both first order logic and natural language understanding as well. And as I mentioned, the system learned, in this case for label C, communication from the contracts dataset, it learned 188 learning expressions, which is quite a lot. And these 4 data scientists, they had half an hour to pick 6 to 7 learning expressions, which they considered to be the best or the most suitable. And we can see that with a human expertise applied after this neural network learning or after machine learning, and actually smaller and more interpretable set could be created, which is even more described by this experiment. What they did is that they had these 4 people and they took all groups of 3. So this resulted in 4 different teams. You can see that this one is the group without A, without B, C, and D. And they combined, in all 4 cases, they combined the linguistic expressions, the LEs, from those 3 people in the group. And that's what they call them a model. And then they tested these models against the best performing other approach against the LSTM. And you can see that except for one group, like without A, yeah, it turns out A was pretty good. But without A, it was comparable to LSTM. But all the other 3 groups, if combined, all the knowledge from all the 3 people and from the machine, it actually did outperform a lot the or significantly this LSTM model. By the way, this one here is not the same metric anymore. So you might ask, how come that we have 0.4? We had almost 1. It is because this time it's F measure, and the other metric was this under the precision under the precision recall curve. Exactly. The other thing which I spoiled a bit, what people also did was that they saw that, well, this rule does make sense, but why should it be in future tense? Like, that does not make sense at all. So they just took it and they said, well, that's a better rule. Like, probably not on the data set and not on the test set, but generally it's a better rule because they know the domain and they know how that should work. So there's not much left. Probably a summary about the paper again. So what was it about again? It was so this paper proposed a neuro-symbolic learning method for sentence classification task. Compared to similar methods, it performs better, more efficiently, better in both in efficiency and quality. The key findings of this paper is that yes, it is possible to learn human interpretable models if we keep explainability in mind from the beginning. Yeah, this model, it can actually be used for any multiple instance learning tasks, assuming that the predicates are given. So that's, in my opinion, that's still quite a pain point, is that you have to do this lot of pre-processing before. You have to have the predicates in order for this network to function. And also, in a more general way, it can actually, not 2 times can, it can learn rules combining any previously built classifier's output probabilities. So let's say you learn probabilities with whatever classifier you have, but they are just probabilities. You want to combine them to rules that are actually good, then their proposed algorithms is a good way to do that. A disclaimer which they wrote that their approach is actually different from the approach of explainable AI, because it's more like doing the model in a way which is explainable. So this one it still has this black box part of this neural network, learning weights, optimizing and updating random stuff. But what comes out in the end is still explainable. What are their perspectives? They want to learn these rules on top of embedding. So now they learn on top of predicates. But yeah, as I mentioned, it's probably quite tedious to create those predicates. So it would be easier just to apply embeddings. I don't really get it how, so they didn't describe it. And the other one is also, which is still a kind of black box to me, this whole dictionary pre-dictionary creation. So one approach would be just to learn these, not just the rules, but the dictionaries also jointly. It's probably a way bigger task to do. Okay, in the last minutes, how is it related to my research? I'm currently doing my research on the BRISA data, which are building regulations and its legal tasks. So it's highly structured, and in our opinion, there's a great potential for rule learning. We already have rules defined as graph and text patterns, and these patterns are defined on, the graph patterns are defined on UD or Forlang semantic representations. And a potential or experiment could be to either to change this graph representation to this predicate argument relations that we saw now, or combine Forlang with this approach, or actually Forlang is already this approach, so I'm not 100% sure though. Oopsie, that was strange. Yeah. Some challenges that I see if we wanted to apply this approach as it is to our dataset is the language, because this propositional bank is originally done for English. I saw that IBM actually has a repository, this system T, with universal propositions, And I also saw that there is for German, and there's something done for German, but the system T branches for separate languages, they all use the English categories, just everything translated to German. And it might cause this problem because German verbs that do not necessarily have the same arguments as English verbs, or there are like grammatically there are other stuff to consider when you're talking or using German than when you're using English. There are these different cases and so on. So that's definitely something I would have to look into if I wanted to use them. And just the last slide is about what's still unclear for me after having that or having spent 2 weeks for understanding this article, how the dictionaries are constructed. So they wrote something about the T-Reg data that automatically capture surface form that discriminate well among labels. So they didn't elaborate how they did that, but I think they tried to already cluster somehow the words and to create clusters that are very specific for one specific label, and they use that as a dictionary, as separate dictionaries, I guess. How the semantic or the syntactic parse is implemented, they're talking about shallow semantic parsing, but they also use syntactic parsing stuff like the tense or the voice of the verb. It's probably not that difficult to find out, but they didn't mention how they did that. Also, this semantic parser is also some internal IBM tool. How these facts and predicates are constructed, given the dictionaries and the semantic notation, that's also, I had a theory that they just combine everything with everything, but I'm not 100% sure, and I also didn't find any clue in the paper with this regard. And also, probably you saw that at the beginning we had sometimes within one predicate we had an or relation, a disjunction, and I'm not really sure how they did that. Because it's not, they only talk about how they did the and relations. And I have a guess, I think it's just a syntactic sugar for the contains, in case a dictionary has multiple elements. So it does not say that it contains and a lot of words, but they define that it is either A or B or C. And that's my guess, but it wasn't explicitly described. And the last thing, I think, no, the one before. Yeah, I think I already mentioned this one. There's this K. Why is it good to have multiple of these CGM modules? Because the number of the E's coming out in the end, that's a result of the algorithm and has nothing to do with the number of K. Although they referred all the time, yeah, K is the number of LEs, but it's actually not. And I'm not sure. I think it's probably for the algorithm to converge. If you have more of these modules, and because in the end you just take a maximum of all of this, I think it probably makes it faster to converge, but it also wasn't explicitly described, so it's just a guess. And the last one is, yeah, generally the term of LE is a bit overloaded. Like I wasn't sure whether they mind the output of a specific model or the logical form, or what is one LE? Is it like, is it a conjunction or also disjunction of conjunction? So I think I got it, but sometimes it was a bit confusing. And yeah, those are just references. And now thank you for your attention. I think I will stop the recording and then we can discuss. Oopsie. I just need this one. Yep. Stop.